Good morning. Am I audible? Am I audible to you? Nilesh?
Yes, sir.
Okay, thank you. So today we would be start the topic square wave generator. In the last lecture we have learned the Schmidt trigger, that is also one kind of the square wave generator. But here today we would be going to learn the free running square wave generator, that is also called as the R-stable multivibrator as well. So R-stable multivibrator is an considered as a square wave generator here. In the circuit of this stable multivibrator, the output of op-amp is fed back to the non-inverting input terminal, and the resistors R1 and R2 form a voltage divider network, and you can consider a fraction, that is R2 upon R1 plus R2 of the output, that is being to fed back to the input. In this way, you can say the output can take a value of plus beta Vsat or minus beta Vsat, and these voltages plus minus beta Vsat act as a reference voltage at the non-inverting terminal. So you can see this diagram, that is a diagram of the square wave generator, or you can say the R-stable multivibrator. So please note down this diagram. Here you can see that the output voltage is fed back through the feedback path that consists of the resistance R1 and R2 here, and the voltage at this point, that is considered as a reference voltage, that is beta V0. Beta is what? R2 upon R1 plus R2. That is your beta feedback factor, you can say. So, and it is applied to the non-inverting terminal, and at the inverting terminal there is a feedback resistance R, and there is a input side, there is a capacitor C is used. Okay, so there is no external voltage source has been applied. It would be, you can consider it acts like an oscillator. So generally in the oscillator what happens, there is no input is required to generate the output. A positive feedback would be that would be regenerate the signals. So here the voltage across the capacitor is considered as a Vc, and this capacitor and feedback resistor R would be make a that is called as RC component, that would be decide the frequency at the time period of the output signal. And you can see side by there is a waveform of output and capacitor terminals is also shown. So this square wave is nothing but a output waveform, and this integrating, or you can say the exponential rising and decreasing waveform is the nothing but the output voltage across capacitor Vc. So we would be discuss this waveform later on. First of all, we would be describe the circuitry in detail and find out the equations for the output voltage as well as the Vc voltage across the capacitor. So here the output is connected to the inverting terminal that we have discussed through an integrating low pass RC network. So this resistor and capacitor would be formed a low pass network, and when the voltage Vc across the capacitor would be exceed the reference voltage V reference, switching takes place, resulting in a square waveform. Means the switching would be take place between the plus Vset to minus Vset. So to understand the operation of this circuit, let us consider first initially the voltage at the output terminal is plus Vset. The capacitor C with the voltage Vc start charging through the resistor R towards the plus Vset. This is the initial condition. The capacitor would be start to charging. And the voltage at non-inverting terminal or positive terminal is held at plus beta Vset, and that would be use the network of R1 and R2 potential divider network. So here you can see through the diagram of the waveforms as well, the charging of capacitor C continues until the voltage at the in negative or inverting terminals is just greater than the voltage at positive terminal, that is plus Vset. So this is a just like a comparator like structure. So the comparison of the voltage between the inverting and non-inverting terminal. And when this happens, if the non-inverting terminal is lower than the inverting terminal voltage, that is you can consider in the point of this B, the output is switched to the from plus beta Vset to the output is switched from the plus Vset to the minus Vset, and voltage across the capacitor would be switched from minus beta Vset towards the plus beta Vset towards the minus beta Vset, but it is not immediately as the output of the square wave generator. It would be going decreasing very slowly because it would be take the time to discharging the capacitor. So the voltage plus beta Vset or plus beta V0 across the capacitor now start discharging through the resistor R, that is the feedback resistor, and charging towards the minus Vset. So the capacitor voltage Vc now becomes increasingly more and more negative, and it would be reached to the point that is called here, shown here, that is point C, when your Vc would be exceeds minus beta Vset, and when it would be exceed from the minus beta Vset, again the output would be switched from minus Vset to the plus Vset, and this cycle would be repeats. So depending upon the voltage across the capacitor with reference to the reference voltage, there is a comparison would be performed. So according to this, your output voltage would be switches between the plus Vset to minus Vset or minus Vset to the plus Vset, and this cycle would be continuous, and you would be get a free running output waveform, that is nothing but a square wave. So we can summarize the operation in 2 points. First of all, when the output initial condition, when output is plus Vset, the capacitor C charged from minus beta Vset to the plus beta Vset, and the output switches from plus Vset to the minus Vset. Second case, when output is at minus Vset, so capacitor charges from plus beta Vset to the minus beta Vset, and it switches the output to the minus Vset to the plus Vset. So in this way, switching would be happen. Now, as per the output waveform, we have to be calculate the period and the frequency of oscillation. This structure is also called as a relaxation oscillator as well. So in this case, the frequency of this free running multivibrator is determined by charging and discharging time of the capacitor between the voltage levels minus beta Vset and plus beta Vset, or vice versa. So here we have to be analyze this. You can see so here if you have to be see that the voltage across capacitor would be considered as a function of time, that can be represented as Vct is equal to V final plus V initial minus final into e raised to the power minus t upon Rc. Why it is e raised to the power minus t upon Rc? Because it is a voltage across the capacitor is exponential in nature. So here VFIN fin is nothing but the final value of the voltage. VINI is nothing but the initial voltage of across the capacitor. So considering the charging and discharging of this capacitor from the point A towards the plus V set, you can say that or rewrite the equation as VCT is equal to, it is initially at the plus V set, so plus V set plus voltage across the capacitor is initially minus beta V set, then minus the final voltage plus V set E raised to the power minus T upon RC, which could be further deducted as VCT is equal to V set minus, you have to take the V set common, 1 plus beta E raised to the power minus T upon RC. This is equation number 2. Okay. So in this way we can write the equation of the voltage across the capacitor, because it is a deciding factor for the time period and the frequency. Now further, according to the waveform, we have to be elaborate this equation. So this is the waveform of the output. You can see that here at the time t equal to t1, t small t is equal to capital T1, at that time the voltage across the capacitor would be reaches to plus beta V set, and it would be switches from A to the B point. Therefore, the voltage, capacitor voltage Vc at T1 would be equal to, simply you have to be in the equation number 2, put up the value of VCT is equal to plus beta V set. So it would be become V set 1 minus 1 plus beta E raised to the power minus T1 upon RC. So we have to be just substitute this value of VCT and T is equal to minus T is equal to T1, and V set is taken common through all the equation the RHS side. So that would be further written as V set would be cancel out on the LHS and RHS side, and you can see here it would be came as 1 minus beta is equal to 1 plus beta E raised to the power minus T1 upon RC. That would be further written as you can take this 1 minus beta upon 1 plus beta, take the log, natural log on the both sides, it would become ln 1 minus beta upon 1 plus beta minus T1 upon RC. When minus sign would become to the LHS side, it would be become natural logarithm 1 plus beta upon 1 minus beta is equal to T1 upon RC. So T1 is equal to what? RC into natural log 1 plus beta upon 1 minus beta. That is further you can write as RC ln beta is what? R2 upon R1 plus R2. So 1 plus this and 1 minus R2 upon R1 plus R2. That would be further reduced to the RC into natural log R1 plus 2R2 upon R1. So this is equation number 3. This is the time period of the square waveform. It is half of the time period actually. The complete time period is twice of T1. So that would be further. Please note down these equations as well simultaneously, that when I am explaining it. So further you can write it as total time period is given by T is equal to twice of T1 2RC ln 1 plus beta upon 1 minus beta. So this is the equation, very important equation here to define the time period of a square waveform, that is output, which would be further written as 2 of RC in ln R1 plus R2 2R2 upon R1. And we see that here in the waveform the output is symmetrical one, hence we can also calculate the frequency because output is symmetrical. So you can find the frequency of this oscillation is f is equal to 1 upon t, that is 1 upon twice of RC ln 1 plus beta upon 1 minus beta. Okay. So in this way, you can calculate the time period and the frequency of oscillation as well of this square wave waveform. So everyone note down this equation of 4, 5 and 6. That would be helpful for you for solving the numerical based on this topic. Now, we have to be consider one case, and the case is what? We have to be consider R1 and R2 both are equal. The resistor network that would be formed of potential divider network, that would be equal, and if it would be equal, you would have found that the time period would be changed, means time period would become 2 RC ln 3, and that would be further beta would be also changed, that would become as 0.5, and t would be become 2 RC natural log of 3. That means frequency would be 1 upon 2 RC ln 3, that is 2.2. So frequency of the oscillation would be become 2.2, 1 upon 2.2 RC. This is also one of the important relationship by keeping the fact that R1 is equal to R2. So in this way, all the equation shows that the time period is directly proportional to the time constant, that is RC. That means varying either the resistor R or capacitor C could be responsible for the changing the time period correspondingly. Therefore, providing a tunable resistance R paves the way for a continuously tunable square wave generator. By varying the value of resistor, you can vary the square wave generator frequency as well as the time period. Okay, now we would be solve one numerical based on it. So this is the numerical question is there for a square wave generator, as we have seen in the circuitry of the square wave. Assume R1 is 116 kilo ohm, R2 is 100 kilo ohm, plus minus V sat is plus minus 14 volt. So then find the time constant to produce 1 kilohertz output. Okay, so we are aware of the, in the first case we have to be use the formula of 2 RC ln R1 plus 2 R2 upon R1. So here you can find out first of all the value of T. We have to find actually RC. So we would become later on this. First all the terms inside the log. So R1 is 116 plus 200 upon 116, that is 2 RC ln 316 upon 116. Because both are kilo ohms, we have ignored the term of the kilo ohms here. So it would become T is equal to 2 RC. When you have to take the logarithm of this, this would be came nearly equal to 1. So T would be become 2 RC. Okay. So by using this relationship, you can find out the value of RC. So T is what? It is 1 upon F. So here F is mentioned 1 kilohertz. So here you can find out as the information given, F is equal to 1 kilohertz. So T is equal to 1 upon F, that is 1 millisecond, or 1 into 10 raised to the power minus 3. That is equal to 2 RC. So RC would be equal to what? 1 upon 2 into 10 raised to the power minus 3, that is 0.5 into 10 raised to the power minus 3 second, or 0.5 millisecond. So this is the answer of the first question. Second, they have asked the value of the resistance R only. From this RC, you have to find the value of R. So for this, what you have to do, you have to be assume some value of the C. So C is equal to 0.1 microfarad or 0.01. Here I would be take 0.01 microfarad. So you can calculate the value of R easily. So it would be 0.5 into 10 raised to the power minus 3 upon 0.01 into 10 raised to the power minus 6. And when you have to be solve this, it would be came as 50 kilo. The third question is here, the maximum value of the differential input voltage. So what is the value of the input voltage is range is here, that is plus beta Vsat to the minus beta Vsat, means it is twice of beta Vsat. So you can write as maximum value of differential input is twice of beta. Beta means what? R1 plus 2 R2, no, sorry. R2 upon R1 plus R2. So it would be R2 upon R1 plus R2. So you have to find out this. 2 into beta Vsat is given plus minus 14. R2 is what? It is 100. 116 plus 100. So it would be came as, for the solve view, it would become as 12.96 volt. So maximum value of the differential input is 12.96 volt. And if you have to be going to say the peak value of this, peak value of differential input, because it is in both sides of the reference axis, minus side and plus side, it would become, you have plus minus 2 into half of this is 6.48 volt, means 6.84 volt at the positive axis and 6.48 volt at the negative axis. Okay, so this is the way that you have to be solve the numerical. Some another numerical could be asked, like the designing of the square wave generator. We would be take the problem but solve when the time would be remain for the total lecture. Before this, please note down this problem only. We would be solve it if the time permits. Otherwise, we have to first of all see the triangular wave generator. So design a square wave generator oscillator for F0 is equal to 1 kilohertz using 741 op-amp and the DC supply of plus minus 12 volt. So we have to be moved to the next topic, that is triangular wave generator. So in the previous circuit, that is the relaxation oscillator or square wave generator, we have seen that the capacitor voltage Vc has a nearly triangular wave shape, but not exactly the triangular wave. Why? There the sides of the triangles are exponential rather than the straight line. So to linearize the size of the triangles, it is required that the capacitor be charged with constant current rather than the exponential current through R. So in this circuit, an op-amp integrator is used. So we are to make it triangular waveform. So we have to use op-amp as an integrator circuit is used to supply a constant current to the C, so that output is linear. So this is a circuit, one of the possible configuration of the triangular wave generator. So here you can see that there is a two-stage op-amp is shown here, and in this circuitry, if you have to be refer, there is a two op-amps A1 and A2, and the first stage is nothing but a comparator, and the output of this comparator would be given to the input of the A2, that is the integrator circuit. So A1 is what? Non-inverting comparator, that is just nothing but a Schmitt trigger, and the output of this Schmitt trigger is given to the input of the integrator circuit, and that would be further result as a triangular wave generator. You can see in the waveform, instead of exponential rising the waveform, there is a linearly triangular waveform along with the square wave. Because first stage would be produced square waveform and second A2 would be produce a triangular waveform. So we would be see the explanation of this first. So here, if you have to be see, two op-amp A1 and A2 is used, and A1 is a non-inverting comparator and A2 is the integrator circuit. Op-amp A1 is a two-level comparator whose output is determined by the plus minus V side, and the square wave output from the A1 is applied to the inverting terminal of the integrator circuit. So here, the output of A2 is a triangular waveform and it is fed back as an input to the comparator A1 through the voltage divider network R2 and R3. So we have to analyze this loop, this feedback loop. So when you would be going to analyze this feedback loop, so we have to first consider that the output of the A1, that is V0 dash, is initially at plus V set voltage, and the integrator then integrates plus V set and produces a negative going ramp signal at its output. Negative going ramp signal. This is the negative going ramp signal. So hence the voltages at the two ends of this voltage divider network formed by the R2 R3 resistor are plus V set at the output of A1 and at minus V ramp at the output of A2. So one end there is a plus V set, another end is a minus V ramp of this loop that is formed by the voltage divider network of R2 and R3 as well as the output of A2. So if you have to see the waveform of this triangular wave generator, so you would be found that at the time T1, this is the time means T1, T is equal to T1, when negative going ramp reaches to a value of minus V ramp, that is represented here with the point of A, the effective value at P, there is a voltage divider network, become slightly less than 0. And when it would be slightly less than 0, this would be switch the output of op-amp A1 to plus V set to the minus V set. So it would be switched at this point A, it will switch the output plus V set to the minus V set. So here at the output of A1, that is the first stage op-amp, would be reached to the minus V set, and at that moment the op-amp A2 start integrating and increases its output in the positive direction. So because of that, what happens, it would be start to integrate, means the ramp signal is rising towards the positive direction. So at time t is equal to T2, it would be rises and reach to the point B, and the voltage at the point P becomes now just more than the 0 volt. So at that time what happens, again it switches the output from the minus V set to the plus V set, and when once again it would be switches the value of output of the A1 plus V set, again it would be going to output of the A2 would be become decreasing and generating the minus V ramp signal, and this cycle would be continuous. This cycle would be repeats itself and generate a triangular waveform. So the frequency of the waveform is determined by basically a RC value of the integrator. So what is the integrator? This is the integrator one. So its RC value would be decide the R1C1, the frequency of the waveform of triangular waveform, and saturation voltage would be plus minus V set of the comparator op-amp A1. So we have to first find the amplitude and frequency of the triangular waveform. So you have to be found that when comparator output is at plus Vset, effective voltage at the point P is minus Vref. Remember the circuit, it would add the voltage when it would be at plus Vset, the voltage at P is, so it is voltage is R2 upon R1 plus R3 Vsat, this terminal voltage minus Vref, this terminal voltage, plus plus the voltage at output of A2, that is minus Vref. So it is written as minus Vref plus R2 upon R2 plus R3 Vsat minus Vref, because output of A2 is nothing but minus, so it would be minus Vref. The loop voltage would be equal to 0. Simplifying, we would be get minus Vref is equal to minus R2 upon R3 plus Vsat. So you can write equation 1 and then equation number 2 here. At time t is equal to T2, when the output of A1 switches from minus Vsat to plus Vsat, the Vref would be equal to minus R2 upon R3 minus Vsat. It would be R2 upon R3 Vsat. This is equation number 3. So this is at t is equal to T1 and this is at t is equal to T2. Okay. So the peak to peak value of the amplitude of a triangular waveform would be become V output peak to peak Vref minus Vref is equal to twice of R2 upon R3 Vsat. Okay. So this is the peak to peak voltage of the triangular waveform. Now we have to find out the frequency of this waveform. So for that we have to be analyze the voltage across the indicator. So here the time taken for the output of A2 to switch from minus Vref to the plus Vref is half of the total time period, that is T upon 2. For the basic integrator output equation, we know that V0 is equal to minus 1 upon R1 C1, because inverting integrator is there, so it is minus sign is there. Integrate 0 to T upon 2, half of the time period, minus Vsat dt. So it would be Vsat upon R1 C1, the time period is T upon 2. So this would be fifth number equation here. And that could be further written as the equation for the time period T, 2 into R1 C1 output voltage peak to peak upon Vsat. So this is also a very important relationship. Through this relationship of the time period, you can find out the value of time period in terms of resistance R2. So it would become as, substituting the value of output voltage peak to peak from the equation number 4 in the above equation number 6, you would be got the value of T, that is 4 R1 C1 R2 upon R3, and from that you can find out the frequency of oscillation. F0 is equal to 1 upon T R3 4 R1 C1 R2. So this is the frequency of oscillation for the triangular wave generator. So these two formula would be useful for finding out the solving the numericals based on this topic. Now we have to see one alternating arrangement for triangular wave generator. That is nothing but we have to use a two-stage op-amp once again, and output of this square wave generator is directly given to the input of this integrator. So you can see that in the previous case we have given the output of comparator, but here we have to simply use the square wave generator, that is we have used in the previous sections topic. Same structure is used here as an input stage, and the output of this square wave generator, this is a square wave, is directly given to the input of this integrator, and finally we would be get a triangular waveform. So this is also one of the possible alternative structure of the triangular wave generator. Please note down this diagram or take the screenshot. So here what we have done, you can assume that the voltage of first stage, that is V0 dash, is high as at plus Vset initially, and this forces the current plus Vset upon R. What is the current in this network? Current in this network is V0 dash upon R3, that is Vset upon R3. This is the current on this network. This current would be flow through the capacitor of this integrator network. So this feedback capacitor of this integrator, and producing a negative ramp voltage at the output of this integrator V0. And when V0 dash is low at minus Vset, the output of the integrator would be ramps up linearly. So in this way, the cycle would be continue. So initially, when V0 dash is at plus Vset, your output voltage across the A2 would be at negative ramp, but V0 dash is minus Vset, it would be increasing or rises up to the plus V ramp. So the cycle would be repeated itself, and hence the frequency of the triangular wave is same as that of the square wave waveform frequency. Here we have connected the R in the square wave generator of the circuit to determine the frequency of the triangular wave. Means in the first stage, whatever the resistor we have used, and amplitude of the triangular wave decreases with increase in the frequency value, and this is due to the fact that capacitive reactance decreases at high frequency and increases at the low frequency. So in this way we have generated the square waveform along with the triangular waveform. But there is a one condition, that to get a stable triangular waveform, you have to maintain the condition 5R3 into C2 should be greater than T by 2. So the T is the period of the square wave input. Okay. So this is all about the triangular waveform wave generator. This is the numerical. Please note down this numerical here based on this triangular wave generator, and simultaneously you have to start to fill up the attendance. So in this way we have completed the unit number 5. So there are 2 unsolved numericals remaining because of the lack of the timing. So you have to be the task that you have to solve this numerical. If you have any issue or problem, you can ask me related to this numericals or related to the topic we have learned today. From tomorrow we would be start the unit number 6. Okay, thank you all of you.